Alright, so let's go ahead and start everybody equally off dead.
In the previous video, we started building the control logic for a computer, and we started by building a counter that counts through each step of our instruction cycle. Because each instruction that we want to define for a computer, whether it's load A, add, output, each of those instructions is made up of up to five, or really it's always five, although sometimes the last steps don't do anything, but it's five different micro instructions. And this counter counts through from 0 to 4 to keep track of which step we're on. And what we saw is that for T0 and T1, those first two steps of the microinstruction, those are always the same, regardless of which instruction we're actually trying to execute, because those two steps are the steps that fetch the instruction from memory and put it into the instruction register. And so in fact, we were able to sort of temporarily wire those up just by manually connecting these signals for T0 and T1 through an inverter to the appropriate logic signals here on the control word. But what I want to do in this video is replace this kind of temporary demonstration here for those first two steps with logic that's going to be able to carry out all of the steps for any instruction that we might want the computer to be able to do. And so in order to sort of understand how that's going to work, there's really kind of two pieces of information that feed into what control signals need to be active at any point in time. And one of those pieces of information is which step we're on here. So which of these time steps we're on. So, and that's what we're doing now. When we're on T0 or T1, we have signals that indicate that. But that's one piece of information. And so where we are in this count is one piece of information. But then the other piece of information, once we get into T2, T3, and T4, is going to be different based on which instruction we're actually executing. And so that piece of information is here in the instruction register, because by the time we get to T2, these first two steps will have loaded the appropriate instruction. So if the instruction is load A, that instruction is 0001, we'll have a 0001 sitting in the instruction register. So we have that information here. So all of the information we need in order to be able to set all of the control signals appropriately is available in a combination of what's in the instruction register plus where we are in our count, so where we are in the actual instruction cycle. So one way to look at what we've got so far for time T0 and T1, we're saying for T0 we're doing counter out and memory address register in, and that actually doesn't matter which instruction we're executing, because really at this point in the process we don't even know what instruction we're executing. We have to fetch it from memory first. So at T0 we're doing these things. So another way to look at that is kind of with a truth table here, where we say we have the instruction, which instruction is loaded, which is 4 bits, and then we have the step, which is 3 bits, and that counts from 0 to 4 in binary, because each instruction cycle is 5 clock cycles long. And so another way to kind of look at this is to say, well, regardless of what instruction, so we don't care what's in the instruction register. For step 0, we want to do counter out and memory address register in. So in other words, our control word over here is going to look like this. We're going to have a counter out, we're going to have that as a 1, and then memory address register in is also going to be a 1. And then the rest of these are all going to be zeros. And so that's what our control word looks like whenever we're at time T0 or at step 0, regardless of what instruction. So that's the same thing we're saying here. So T0, doesn't matter what instruction, those 2 bits are set. Now at time T1, we have these 3 bits set. So RAM out, so we're taking the contents of RAM, instruction register in, we're putting that contents into the instruction register, and then we're also incrementing the program counter, so counter enable. And so again, at time T1, we're at step 1 here, doesn't matter what instruction, because this is the same for every instruction that we're executing. In this case, we have RAM out is set to a 1, and then instruction register in is set to a 1, so we're moving contents from RAM into the instruction register, and then we're also incrementing the counter, so counter enabled is over here, the program counter. And then the rest of these are zeros. Got a little carried away and added an extra 0 there last time, but I forgot I left a little blank there. So this is essentially what we've got now, right? So step 0, we're doing this thing, and step 1, we're doing this other thing. So now, where it gets interesting is, at this point, after we've gone through these first 2 steps, the instruction register now actually has the instruction in it. And so, for example, if our program here was load A 14, the instruction register, the instruction for that is 0001. That's the instruction for load A, which we just made that up, but that's what we're saying load A is. And then the number, or the last 4 bits here is the operand for this, or it's a memory address location that we're loading data from into the A register. But what shows up in the first 4 bits of the instruction register is 0001. So in that case, we have 0001 in our instruction register for the next 3 steps. So that's going to be step 010, 011, and then 100. And then once this step counter here gets to 4, it resets back to 0, which we saw in the last video. And so now in this case, since we have 0001 in our instruction register, we know that we're going to be doing a load A, because that's load A. And so the steps for load A, which we talked about in a previous video, is we want to take the contents of the instruction register out and memory address register in. So we're essentially, if we're doing a load A14, we're moving that 14 into the memory address register so that we can fetch whatever is in that particular location in memory. And then in the next step, we do RAM out. So we take the contents of memory and put it into the A register in. So, in other words, if our instruction register says 0001 and we're on step 2, 010, then we say instruction register out and memory address register in. And then everything else is zeros. And then for load A at time T3, we say RAM out, A register in. So RAM out, A register in, and the rest are zeros. And so that's everything for a load A command. We don't actually need to do anything at time T4. So in this case, we'll just leave all of the signals low. And that way, for that clock cycle, the computer won't do anything. Now the next instruction is add. And add, the opcode for that is 0010. And when that instruction is 0010, we do something different for times T2, T3, and T4. So this case here, this was load A, but for add, the instruction is going to be 0010, and it'll be 0010 for those last 3 steps of the instruction cycle. So this is the add command, and the way the add command works is, of course, we've already gone through, for step 0 and 1, we've fetched the add command from memory, and that's the same for every command. But then for steps, so 0, 1, 2, 3, and 4, for steps 2, 3, and 4 for the add command, well, the first thing we want to do is we want to take instruction register out and memory address register in. So we want to take the location. So if we're saying add 15, we want to go to memory address location 15 and get whatever is in there and add it to the A register. So add 15, so we take the instruction register out, we put that address into the memory address register, and then we take the contents of RAM, so RAM out, and put that into the B register, right? So B in is over here. And then that'll start to add whatever's in A and B, and so we take the sum out from that addition and put that back into the A register, so A in. And so these are the steps for the add command, and I'll just fill in the rest of these zeros.
Here, not necessarily
so that's the sequence of control signals that we want for the add command. And then the last command that we had in this program is the output command.
Keeping it moving.
And so that the opcode for that, we decided was just going to be 1110. So we'll just do that here. That's 1110 will be the instruction that gets loaded if we want to use the output command. And again, that has the same 3 steps. And in this case, the output command is quite straightforward. It just takes the contents of the A register, so A out, and it puts it into the output register. So output register in is right here. And that's it. It only needs 1 more clock cycle. So these last 2 clock cycles are just unused. And you might be able to imagine some ways that you could optimize the computer to skip those in certain cases, but for now we won't worry about that. So I'll just fill in the rest of these as all zeros. Now you might notice this is starting to look a lot like a truth table, where we have inputs over here on the left, which are the instruction register and the step that we're on, and then we have outputs, which are the control signals. And in fact, that's exactly what this is. This is a truth table.